Hi everyone, my name is Pradyumn and today we'll discuss the solutions to ABC, that is AtCoder Beginner Contest 443, and we'll discuss the first 5 problems A to E. Okay, but before we start, I'll tell you about our courses at TLE Eliminators. So if you are someone who is stuck at solving just one or two problems per contest, then these self-paced courses are exactly what you need. So we have divided this course into 4 different levels, so you can start from wherever you are: beginner, pre-intermediate, intermediate or advanced. You will learn the most relevant CP concepts through video lectures by experienced educators, followed by practice problems with guided hints and detailed video solutions that help you understand the why and not just the how. We believe in helping you build real problem solving intuition. And if you are still not sure, like if you are stuck, then you can contact our doubt support. So you'll get instant doubt support from the top rated mentors of this country on Discord, and so you are never left stuck. And beyond just learning, you will enjoy gamified progress tracking, internal contests, and PCDs to keep you consistent. So pick the that fits your goals and start learning today. So let's start with the PCD now. So this was the first problem. You are given a string S consisting of lowercase English letters. Output the string obtained by appending S to the end of the string S. So this is a problem. Like, I don't know why it is a problem, but it is a problem that we have been given a string S, like a capital S, and basically it can be any string, let's say ABCD. So we have to append the, like we have to print ABCDS. Okay, so it is nothing, like it's just basic code. So we have to just take the input of the string and print the string along with S. Okay, so https appends beginners. Okay, so yeah, so the code I'll show for it just for the sake of it. So here's the code for first problem. So string S, C in S, C out S plus the character S, or you can see out S then angular brackets and S, like you can basically these things, right, in place of the plus, same thing. Okay, so yeah, that was the problem A. It was very easy. Then we can go to problem B. So B was that Set Suman, like at the annual Set Suman festival, one eats the same number of beans as their age. Takahashi-kun does not eat beans at any other time. He is n years old at this year's Set Suman, that is 0 years later. At the earliest, how many years later will he have eaten a total of k or more beans from this year onward, including this year? He is immortal, so he will eventually have eaten a total of k or more beans from this year onward. Okay. So what they are saying is that we have, like, currently our age is n, right, and it is the year 0 right now, and we are at a festival. So whenever someone is at a festival, they eat beans equal to their age. So in year 0 we'll eat n beans, in year 1 we'll eat n plus 1 beans, in year 2 we'll eat n plus 2 beans, and so on, because after 1 year we'll be of n plus 1 age, after 2 years we'll be of n plus 2 age, right? So eventually this sum would exceed k. Like we have to find out, like if this is n plus l and the sum of this thing is greater than equal to k, we have to ensure, we have to find the value of l such that this sum becomes greater than equal to k for the first time. Like we have to find the lowest value of l. Okay, so that is the question. Like every year we eat n, like these many beans, and we want to eat a total of k beans, at least k, right? So basically we want that n plus n plus 1 plus n plus 2 up till n plus l should be greater than equal to k. Alright, and here n and k are given, right? So we want to find the value of l, the smallest value of l. Now there is, okay, so you can simplify this, but you don't need to actually, but okay, I will do that. Like, I'll first show the efficient way and then I'll show the easy way. There are two ways to do this problem. So first, efficient way. So like, okay, 0, 1, 2 up to l. So there are l plus 1 terms, right? So this is l plus 1 into n, right? And plus this is what, like 0 plus 1 plus 2 plus up to l. So the sum of first l natural numbers, which is l into l plus 1 by 2, right? So this is basically like, okay, you, and this is greater than equal to k, this has to be greater than equal to k. So this is your equation, right? And you want to find the lowest value of l. So essentially what you can do is, like, okay, l can range up to 0, 1, 2 up till some high value, like let's say 1 in 9, okay, 10 to the power 9. Of course, if l is 10 to the power 9, that is we eat beans for 10 to the power 9 years, then definitely we will exceed k, right? Because the limit on k is just 10 to the power 8. So if we eat, even if we eat one bean every year, then also we'll exceed k if we eat for 10 to the power 9 years. So definitely l is less than 10 to the power 9. In fact, l is much less than 10 to the power 9. But yeah, my point is that, okay, the value of l can start from 0 and be up to, let's say, 1 in 9, right? So, and like, you will get a point, like let's say, basically there will come a point, like when you, if you take l equal to 0, so in this case you will get n beans, right? For the first year you get n beans, then for l equal to 1 you get 2n plus 1 beans, then for l equals to 2 you get basically 3n plus 3 beans, and so on. So after some point, like at some point here, it will happen that you will cross the number k for the first time, right? Like basically for these numbers, this value is less than k, right? But for this number, for the first time, the value becomes greater than equal to k, and we want to find out this value only, right? So you can write this as false, 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 like whether or not this value is greater than equal to k, right? So until some point you will get a false, and then after a value of l, it would become true, right? What would become true? Whether or not f of l is greater than equal to k. So this statement would become true after a value of l, because this function is increasing, right? Like the more years, the more number of beans, right? So this is what the function looks like it is monotonic, right? So you can simply do a binary search on the answer. Binary search on the answer. Okay. Like you have to find the first L such that f of L becomes greater than equal to k. So that is a British standard problem of binary search on answer. And you can do that. Okay. So it would take only like log of 1 in 9 time. Log of 10 to the power 9, because this check function, basically you will just, let's say if you want to check that does the value L equals to mid satisfies or not. So for that you will simply put it in this equation and check if it is greater than equal to k or not. And if it is, then you will do something, and if it is not, then you will do something. So your check function is just O of 1. So your complexity would be log of 10 to the power 9 upon 1 into O of 1, so log of 10 to the power 9. So in like 30 iterations you will be able to find the answer, right? So this is the efficient way that you can apply. But there is one easier way where you don't have to take the summation, you don't have to do all these things, but you just have to observe. Okay, so what you have to observe is that the constraints are up to 10 to the power 8 only. Okay, so what is happening, like for the first year the number of beans is n, then for second year number of beans is n plus 1, then third year number of beans is n plus 2, and so on. Like number of beans is keeps increasing, right? Like initially it is n, then n plus 1, then n plus 2, and so on. So actually so if you take the prefix sum, like let's say for the first, like for the 0th year it is n, then for the first 2 years it is n plus n plus 1, so 2n plus 1, then for the first 3 years it is 3n plus 3, then 4n plus like 6, and so on. So like if you look at the sum, that is 1, 2, 3 and 4, like if I look at f of L is the total number of beans, total number of beans I eat if I eat for L years, right? So if you look at f of L, it is actually quadratic in L. Okay, like what I mean by that is that let's say you have n equal to 1. Okay, so on the first year you eat 1 bean, on second year you eat 2 beans, on third year you eat 3 beans, on fourth year you eat 4 beans, and so on. So after L years you must have eaten L into L plus 1 upon 2 beans, right, which is approximately L square by 2 beans, right? So like the number of total beans that you have eaten is growing quadratically, like it is growing by n square, L square, right? And even if you start with n, so we have the formula right here, which is L plus 1 into n plus this thing, right? So this is also quadratic in L, like this is O of L square, right? So what we can say is like this number is growing pretty fast, like in the year 0 it is n, in the year 1 it is 2n plus 1, in the year 3 it is 3n plus 3. So this number is growing pretty fast. It is growing proportional to L square approximately, right? So to reach 10 to the power 8, like we want to reach at least k, right? So to reach 10 to the power 8 beans, we would take approximately square root of k time, right? Like if my number of beans is approximately equal to L square, right, and I want this equal to be k, so k is equal to L square, so L would be equal to square root of k, right? So only in square root of k amount of time, like only in square root of k years, we would be able to eat that many number of beans. So actually if you just brute force, like just start with n, like start a loop with n, then add n plus 1, then add n plus 2, and so on, like keep adding, then eventually you will reach the sum is greater than equal to k, and this will happen in order of root k time only, order of root k steps. And since root k is just 10 to the power 4, we can easily brute force this. Okay, so this is your solution for B. Okay, so I'll show the brute force code, like I just wrote the brute force code. The like both of them are pretty simple, you can think of it by yourself. Okay, so int nk sin nk sum equal to 0, then I start a variable I equal to n, and I do I plus plus, sum plus equals to I. So if the sum becomes greater than equal to k, then like we want to print this year, like on which year it became greater than equal to k. So on this year where it was I, so year I minus n, right? Because if I is equal to n, then on year 0 it becomes greater than equal to k. So I just print I minus n and I return. Okay. So it will stop. Yeah, so it will stop the loop right here after finding this the print, and this will this iteration, like this for loop, will only go up till root k time, order of root k, right? So yeah, that's the solution for B. Let's go on to C now. Chalk-adder addiction. AtCoder Incorporated starts work at time 0 and ends work at time t. The interval between time t and time t plus 1 is 1 second. Takahashi-kun views the SNS chalk-adder during the AtCoder's Incorporated business hours according to the following rules. He opens chalk-adder at the same time as the work starts. If the chalk-adder is open at the moment Aoki-kun passes behind Takahashi-kun's desk, he immediately closes it. If Takahashi-kun closes chalk-adder at time t, he always opens it at time t plus 100. From the start to the end of the work, Aoki-kun passed behind Takahashi-kun's desk n times, with the ith time being at time ai. From the start to the end of the work, for how many seconds in total was Takahashi-kun viewing the chalk-adder? Aoki-kun never passed behind the desk at the moment when Takahashi-kun opened the chalk-adder. Okay. So what they are saying is that basically there is some private thing. I don't know what chalk-adder is, but there are two people, Takahashi, let's say T, and A. So what is happening is T is sitting somewhere on his desk, okay, and over here a box is there with a flap on it. Just assume it is a box with a flap on it, and T is sitting here, okay. So T is sitting here, and what will happen is whenever A comes, like he will, let's say he comes from here, so whenever A comes, T will close the box like this, okay. Like if it is currently open, T will close the box so that A doesn't see what inside the box, right? And after 100 seconds, he opens it again. Like what T will do is, like whenever A comes to his desk, he will close the box if it is currently open, and after 100 seconds, he will open it again, right? So they are asking that what is the like total amount of time, like if this Aoki person, like person A, visits this desk n times, so they have given the times at which person A visits the desk, right? So they are asking that what is the total amount of time for which the box is open, right? Total amount of time, total time for which box is open, okay. And they have guaranteed that this person A never comes at a point where, like where he's opening the box. Like see, when he comes, let's say the box is open and he comes, so Takahashi would close the box, and then after 100 seconds he would again open the box. So when he's opening the box at that point, Aoki will not come. That is in the input guaranteed. They have promised that in the input, okay. So that is the problem, and like we have to find the total time for which the box is open, right? So let's look at some samples and understand this problem. So like we have 100, 150, or let's copy it. Okay, and the T is given to be 700. So what is capital T? Capital T is the total like time for which the office is open. Like at time t equal to 0, the box is opened, and at time t equal to 700, the box is closed always, okay. And in between that, these things happen. Like Aoki cannot mind his own business, so he will come to our desk and try to see what's in the box, right? So yeah, what will happen is, let's try to find the answer for this test case. So okay, let's make a timeline. So this is 0. At point 0, the box is open, right? So the box is open. Now at time t equal to 100, Aoki came. So we close the box for 100 seconds, right? So this is t equal to 100, and now the box is closed. Okay, so now the box is closed, and now Aoki again comes and peeks our desk at time t equal to 150. But actually right now the box is not even opened yet, right? The box is still closed. The box is still closed till t equal to 200. Okay, so until 200 the box is closed, and then we'll open it, right? So we'll open it, it's opened, and at 300 again Aoki visits, and then we'll close the box until t equal to 400. And in between, if you can see, this 350 pivot Aoki came, right? And then again at 400 we'll open the box, right? So we've opened the box now, and until 700 no one comes, and at 700 this Aoki comes, right? But now at 700 the day is overall, like the day is over. So this is the timeline of the day, right, from here to here. So in the entire day there were 700 minutes, and out of those, these 100 minutes were closed, like from 100 to 200 and from 300 to 400. These times were, the box were closed. So for basically 200 total seconds, 200 minutes or seconds, whatever it is, 200 units of time. Okay, 200 seconds. So for 200 seconds the box was closed. Okay, so for the remaining 500 seconds the box was open. Alright, so that's why the answer is 500. So this is your problem that you have to solve, and it is just simulation, right? Like basically you just iterate over the array and just implement something. Okay, like actually you cannot really do it in order of t. Like if you try to imagine ki you just like let's say you put I equal to 0 and then keep doing I plus plus until you hit 100, and then again you open the box, then you will do I plus plus until you hit 200, and then the guy comes. So but like basically you cannot iterate over time. You can't iterate over the entire time. Like basically if you cannot do it in O of t, because O of t is not allowed. The constraints on t are very large, 10 to the power 9, right? So instead what we can do is we can try to like iterate over the array, that what are the moments where Aoki comes to our desks, and then we can maybe calculate something, right? So let's say this is the input, right? So what will happen is at time t equal to 0 we opened the box, right? So from 0 to 100 definitely the box is open, right? So for 100 seconds the box is open. Now we close it because Aoki came, so we closed it until 200, right? And in between 150 also came, but we don't care about that because we closed it at 100. So at 150 also it is closed, right? Then so basically yeah, we closed it at 100. Then 150 came, so for 150 we don't care about 150, right? Then what happened? 300 came. So in between this 100 and 300 there were 200 seconds, right? And out of those 200 seconds, for 100 seconds it was closed. Like basically it happened that we were at 0, then until 100 it was fine, it was open. Then at 100 we closed the box, and at 200 we opened it, and then at 300 Aoki came again. So like at 100 Aoki came, and then at 300 Aoki came. This 150 also Aoki came, but we'll ignore that because at that point nothing happened, right? So at 100 Aoki came, and then at 300 Aoki came. So in between those 200 seconds, the first half, like the first 100 seconds, it was closed, right? And next 100 seconds it was open, right? So basically 300 minus 100 and minus 100 because it was closed for 100 seconds, right? So for this much time the box was open. So for 100 time box was open, right? And then at 300 again we close it. So at 300 again we close it. Okay. Then Aoki again comes at 350. So but 350 is still closed. Like the last time we closed it was 300. So at 350 it is still closed, right? And then after that he comes at 700. So at 700 it is open, but so yeah, in between there were 400 seconds, but out of those 400 it was closed for 100 seconds. So basically for 300 seconds it was open, right? So he came at 700, and then till the end of the day he did not come again. But this is the end of the day only. 700, like t equal to 700, right? This capital T is given to be 700 in this case. So this 700 was the end of the day, right? So yeah, the final answer would be 100 seconds here, 100 here, and 300 here, right? So we have 500. And like this is how we can find out the answer in O of n. Like we can simply keep track of when was the last time that we closed the box. Like here 100 pe Aoki came, so we close the box here and we mark a variable that at 100 we closed the box, right? And then next time at 150 he came, so we'll check that the last time that we closed the box, was it more than 100 seconds ago or less than that? Like, is the box still open and closed? So if the box is still closed, then we won't do anything, we'll continue. So then we will go to 300. So since this 300, at this 300 point, like since this 300 minus last closing time, that is greater than 100, right? That is greater than 100. That means our box is open at 300, right? So we will just close it again. So the last closing time becomes equal to 300. But before that, we will add to our answer 300 minus last closing time minus 100, because this is the time frame between the two visits, and for 100 seconds it was closed. So for 300 minus LCT minus 100 it was open, right? So we'll add this open time to our answer, right? So we'll do this until here, and then finally until time t. So if t minus LCT, if that is greater than equal to 100, then also we'll add t minus LCT minus 100. Okay, this is the rough solution of this problem. I'll explain sample test case 3 as well, or okay, it is too large to explain, but I think you understood, right? That we can simply maintain the last, what do you say, closed time. That what was the last time that we closed the box, right? And simply you can check that is the current time more than 100 plus the closed time, and if it is so, then the box is open right now, and then you will close it again, right? And update the closed time and also update the answer. Okay, that is the entire idea. So let me show you the code for this. Okay, so int nk, c in nk. First of all, if n equals to 0, then c out k. like n equal to 0 is also there in the constraints. So if n is 0, then like all of the, like for all time, the box is open, right? So you will just print the entire day's time. Then I'll take the input of the array, long answer equal to 0, and answer plus equals to a naught. So why a naught? Because from time 0 to a naught the box was open, right? So I'll add a naught. Then last closed time, LCT, this is a naught. Like at a naught we close the box. Then for I equal to 1 to n, if ai is greater than last closed time plus 100, that is, if at the point ai the box is open, then we will close it. So last closed time becomes ai, and before that we'll also increment the answer, that from ai minus, like from the last closed time until now, for how much time the box is open. So that is ai minus last closed time minus the amount of time for it is closed, so minus 100, right? We'll add it to the answer. And also finally, after the last visit of Aoki, the box will open after 100 seconds, like until the end of the workday. We also have to count that, right? So if the end of workday is greater than last closed time plus 100, then ans plus equals to k minus last closed time minus 100, right? So, and finally just print the answer. Okay, so this is the solution for problem C. Okay, so let's move on to the D now. Pawn line. So there is an n by n grid, and there is one piece placed in each column. The piece in column I is placed in row I from the top, row Ri from the top. You can perform the operation 0 or more times. Choose a piece that is not in the topmost row and move that piece to the cell directly above it. Find the minimum number of operations needed to satisfy the following condition for all integers I, satisfying I goes from 1 to n minus 1. Let the piece in column I be in row X from the top, and the piece in column I plus 1 be in row Y from the top. Then absolute value of x minus y should be less than equal to 1. Okay, so what they are just saying in the problem is that we have a grid. Okay, we have a grid of size n by n cross n, and there is one coin in each column. Okay, so like there is one coin in each column. Basically for the column I, the coin is located somewhere. So let's say in the row Ri. So let's say for the first column it is here, for second column it is here, for third one it is here, for fourth one it is here, and for the fifth one it is here. Okay, and sorry, in between I lost a column, so let's say it is here. Okay, so what we have to do is, in one move we can move one coin one step up, right? So from here I can move it to here, or from here I can move it to here, and so on. But like if it is already at the top, then I cannot move it up. Okay, obviously. So I have to ensure that for any two adjacent rows, the coins are adjacent. Okay, like I want the vertical distance of the coins to be less than equal to 1. Okay, like let's say for these two rows, like for these two columns, these coins are a distance of 2 apart. Like they are at a distance of 2 in the y direction. So I have to move this coin upwards so that they come together like at a distance of 1. So I want the distance to be either 1 or 0, right? Like basically less than equal to 1. Alright, so for all the adjacent pairs, like for these two rows, these two rows, these two rows, these two rows, and these two rows, like basically for all the rows, I want to columns, these two columns, these two columns, these two columns, these two columns, and these two columns, I want to ensure that for all these adjacent columns, the coins are touching each other, like either like this or like this or like this. Okay, so what is the minimum number of moves to do that? Like in one move we can take any coin and move it one step above, right? So what is the minimum cost or minimum number of moves to do this? Okay, so first of all, you might think ki, okay, let's say we have the first coin here, so let's move this coin upward. So until, like, this coin is down, right? This coin is down currently, so let's move it upwards until it becomes adjacent to this, like it becomes close to this one, right? So let's say we do that. Okay, so I bring it until here. Okay, and assume that, let's say the input was like this. Okay, this was the input. All right, so let's say that you might think that, okay, let's traverse from left to right in the columns, and since this is here and this is here, we have to fix this, right? So for that we will increment this one above, right? So if I move this here in one move, they will become adjacent, right? Then you will check this one and this one, right? So for that you will bring this even more up, like you will bring it here. So now these are adjacent, but now you can see that this is not adjacent to it, like this coin is no longer adjacent to this coin. So actually what can you do? Like if you are moving from left to right, of course you cannot move it, right? Like if your algorithm says that you move from left to right and then just adjust the coins, then I don't think this would work, because it might mess up the previous ones, right? So what can we do? Like this algorithm is not correct, obviously. Okay, so what can we do? Now one thing to observe in this problem, like it's just intuition, that whatever you have the topmost coin, like see, you can only move coins upwards, right? You cannot move them downwards. That is the point. So if you move them upwards, and like the topmost coin, like basically out of these n coins, here n equal to 6 hai, so out of these n coins, whatever is the topmost, like either a single one or multiple ones, let's say this one also top. Okay, so both of these, so whatever is at the top, we will not move it above. Okay, like my point is that it is pretty obvious that whatever coins are at the highest level, of course we won't move that, like of course we won't move them even higher. Okay, like even though in this case we cannot do that, like in this case it's not possible to move them upwards, but even if they were like one cell below, like let's say it was here and here, but still in no world would we move them upwards by one cell, because in that case everything else also would have to move upward extra, right? Like there's no point. We are just making them more far from these adjacent elements, right? So the point is that we would never increment the elements at highest row. Okay, so in this case there are two elements at the highest row, so we will not increase them at all, right? So basically their positions are fixed, so I am marking them as red. Since their positions are fixed, we will not move them at all. So what this means that their neighboring columns, they have to be like here only. Like see, since first of all, like I'll look at these two columns for this cell basically. Okay, so first of all, they will all be less than this. I mean, either its neighboring elements would be in this row only, or they would be in less than the row, so in these 4 rows, right? So like let's say for this column, this coin is in the last row, and since we determine that we will never move this coin upwards, so of course this coin has to move until here. Okay, so you will move this coin here. alright, using 3 moves, because you have to do that, right? That is the minimum number of moves that you have to do. It is pretty obvious. And similarly, you will also move this coin upwards. It was previously here, and then you move it here, because if this is fixed, then you have to move it at least this much, right? Maybe even more you will move it, but at least this much you move, right? And for this, its neighboring is this column, so you have to move this cell here, right? So now all the top layer coins, they are satisfied, right? Then what we will do is we will look at the second highest layer. So of course we will not move them upwards as well, like in the coins. Like by now we know that the top layer coins are satisfied, right? So now if you look at the second highest layer, why would we move them up? Like in what case would we move them upwards? We will not, right? Because that would just get them closer to the top layer elements. But the top layer elements, they are already satisfied. Like whatever elements are there in the top layer, they are already adjacent to whatever they want to be. So now in the second highest layer as well, we will not move them upwards. We will never move them upwards. So therefore their place is also fixed. So we will color them red, that your place is fixed. And then for all the adjacent things, like for all the coins, for all the columns in this row, we will look at the adjacent coins. That is for this coin, the adjacent is this one and this one, and for this coin, adjacent is this one and this one, and for this coin, adjacent is this one and this one. So basically you will just look at both of them. So on the in this column we have the coin at this row, which is already adjacent to it, so that is fine. And in this row we have here adjacent to it, so it's fine. And like similarly we'll check for all 3 of them, right? So now the topmost layer, second topmost layer is done. Like we will never move them. Now the third topmost layer, like this cell, again we will never move it, so we can mark it red. And then the neighboring vertices we will check. So this is what you can do. Like you will just start with the highest level and work your way downwards, because you know that you will never move the highest level coins upward more. So you can use that information to implement the logic, right? I hope it is clear. Like if I show a test case, let's say 5 2 1 3 4. Okay, this is your test case. One, 2, 3, and 4. Yeah, so on the first column we have at row 5, then 2, 1, 3, and 4, right? So first of all we will look at the highest row. So of course I will not move it upwards. I will never move it upwards. So I'll have to look at the adjacent columns. So I'll have to move this coin upwards once, right? So one move we did. Then I look at the second highest row, so these 2. So of course I will not move them more upward, so I'll have to move this one upwards twice, right? So I'll move it upwards, and on this side it's already adjacent to it, right? And then for this coin, at this side it's adjacent to it, and for the right side it's not, so we will move it upwards by 1. So here we moved 2, here we moved 1, so we moved 3 in this move. So the answer is 4. Like yeah, we will check this one also, this one also, this one also, but you will see that they are all adjacent already. So the answer is 4, right? Yeah. So this is the algorithm. And like to implement this, basically what you have is an array which is C1, C2 up till Cn, right? That is C1 means that in the first column the coin is at row C1, or like you can say R, the array's name is R, so R1, R2 up to Rn. So for the row I, the coin is at, for the column I, like for a column I, the coin is at row Ri, right? That's what R1 means. So this array you have already, so you want to process like the highest element first, like the topmost cell, right? So actually I will reverse the numbering, like I will number it from n to 1, so n minus 1, n minus 2 up till 1. Okay, and so I will look at the maximum first, like I look at all the coins in row n, and if anyone is there like this, then I will look at the adjacent numbers, and if they are at distance of more than 1, then I'll have to bring them upwards and I'll calculate the answer. So basically I'll also maintain a vector of vector, let's say vi. So what I store is like vi of I means that like vi of I is a vector containing all the columns, like all indices I for which, sorry, vi of I contains all indices j such that rj is equal to I. Like basically let's say we have 1 3 2 3 and 2, so I'll index this 0 1 2 3 4. So my vi of 3 will store this 1 and 3. Okay, so basically all the positions at which there is a 3, right? So let's say if I want to check all the coins at level 3, I can simply look at this vi of 3, right? And actually since you are moving the coins, from here to here, you need to make a set, like a vector of set, that vi of I is a set which contains all the indices that are at a certain level, right? Because you want to erase from that also, erase and insert. Okay, so that's how you can implement this problem. I'll show the code as well. Okay, so the code is int n cnn input the array for int I, and then I invert it, like I just reverse the numbering, because actually I wrote the code according to the reverse numbering and later I realized that, so I just added these 3 lines to invert the numbering. Okay, so ai becomes n plus 1 minus ai, then vector of set of int vi of n plus 1, so vi of a of I dot insert I, right? Then I'll have ans equal to 0. Then for from top to bottom, that is from I equal to n to I equal to 1, if there are some coins in the ith level, so if vi of I dot size, then for all the coins I will look at, like basically for all the indexes, that is in vi of I we have the columns, right? So for all the columns I'll look at its left column and its right column. So if it is more than at a distance of 1, then I will have to move it upwards. So like let's say if my a of x minus 1 is less than a of x minus 1, that means the coin in column x minus 1, in my left column, that is too far down, so I'll have to like erase it from its set and bring it upwards using these many moves, and so update its position. So a of x minus 1 becomes a of x minus 1, and I'll update the vi also. Okay, and similarly for the right hand side we'll do the same, and finally we'll just print the answer. Okay, so this is the problem D. I hope you understood this, and next we will discuss the problem E, but just 1 minute. Yeah, so there's an n by n grid. The cell at the ith row, actually the problem is very long and it is not very comprehensible in the first glance, so I'll just simplify it and tell you that what it means. Okay, so basically we have a grid. Okay, we have a grid where some of the cells are walls and some cells are blank. Okay, so let's say we have this grid. Okay, and so some cells are walls. I'll shade the walls cells. Alright, and some are blank, so the rest are blank. Okay, and then you start from the last row, from the row n minus 1. Okay, so 0 1 2 up till n minus 1. It has size n by n grid, like a square grid, n by n size grid, and you start at a column C. Okay, like they have given the integer C where you start. So let's say you start from this integer C. Okay, you start from here, and they have said that this cell is always blank, like there is no wall on the cell n minus 1 comma C. Okay, so we start from here, and in one move we can either move like in one move we have to go from row I to row I minus 1 always. Okay, so we have to go from row I to row I minus 1, but we can move one step to the left, one step upward, or to the right. Like we have these three options, that if we are at some cell, then either we can go leftward or directly upward or somewhat rightward, right? But like we have to go one row above. Okay, but if there's a wall, then I'll tell you what it is. Like if the cell is empty, then we can directly move into it, there is no problem. Okay, but if there is a wall, then if that wall is the lowest wall in that column, like in this column there are no walls below it, right? So in that case we can break this wall. Okay, if this wall is the lowest wall, then we can break it and move into here. Okay, so if we break it, then this wall would be destroyed and there will be no wall left here. So let's say we move into here. So now there is no wall left here. So actually, let's say there was one more wall here, then also we can go upward and then upward once more. So we can destroy this one as well. Okay, so like this is the point, that you can always move into the free cells, but if you want to move into the walls and destroy them, there should not be any other wall below it in the same column. Okay, so what they're asking is that in the top row, how many cells can you reach? Like which cells can you reach actually? Basically they are saying that if you can reach a cell, then print 1, and if you cannot reach a cell, then print 0. Okay, so for each cell they are asking that can you reach it or not. Okay, so this is the problem. Alright, now actually this is kind of like a graph problem, right? Like you can imagine traversal on a graph or traversal on a grid, right? You might have solved those problems where you have walls and you have a path, you want to find a path or something, right? So it seems like that, but here the walls are breakable. That is the difference. Like let's say if it was normal, like if this problem was a simple problem, that let's say we are at some point and there are some walls and we cannot break those walls, so in that case where can we go? But if we can only move upward, top left or top right, if we can only move in these three directions, then where can we go? In which cells can we reach in the top row? If that was the question, then actually it is pretty easy, right? Because it's just a graph. Like this entire board is just a graph where each cell is a node, like each empty cell is a node, and then you have edges coming out of it. So like you can simply apply BFS on this graph, like just start from here and do a BFS or DFS, and like from here you can go here and here, then from this cell you can go here, here or here, then from here you can go here, then from here you can go here, then from here you can go here, and like this. So basically this is a graph, right? Simple graph problem it would have been if we did not know how to, like, if we could not delete the balls, like if we were not allowed to delete the balls, then it is just a simple BFS problem, right? But right now it is not. Okay, so what can we do for that? Like, what's the main difference here? That we can destroy the balls, right? So actually if we figure out that when can we do that, then again it would become very easy. Okay, like let's say we have this grid only. So the point is that normally what you would do is from here you can only go to here or here, right? But right now, as you can see, you can go to here as well. And why is that? It is because this wall is the lowest wall in this column. Okay, since this wall is the lowest wall in this column, it is definitely breakable, right? So actually we can do a BFS here as well. Like we can go here also in a BFS. But what about this? Like what if we are here and we try to go upwards? So this wall is not the lowest, right? So we cannot go upwards. But now it depends that what if it so happened that we started from here, let's say we were here, okay, then we went and broke this wall, we went here, then we went above, we came here, and then we are trying to move above. So in this scenario we can break this, right? Because now it is the lowest thing, like at this point this is the lowest wall, so we can break it. But if we had come from the other path, like let's say if we had come from here, then here, and then here, and then we cannot break this wall, right? So that is the difference. So now what can we do? Like this is the problem, right? That from this node, do I make an edge to this node or not? That is the entire question. Like, should I make an edge from this node to this node or not? Because in some scenarios, like if you come from here, you cannot delete it. But if you come from here, you can delete it, right? So actually, sorry, from here you cannot go leftward, but still you just the same logic. Like let's say these walls were one up, okay. So my point is that if you go like this, you can reach here like this also, and also via breaking this wall. So if you reach it like this, then you can move into here, but if you reach it like this, then you cannot move into here. So then what should you do? Should you add an edge between this node and this node, or should you not add an edge between this node and this node? That is the main issue here. But what I am saying, like, so how do we solve it now? How do we solve the problem? So actually what you can think about is that, okay, I know that if the wall is lowest, if the wall is lowest in the initial board, then it is definitely breakable. Then it is definitely breakable. Okay, that is for sure, right? If the wall is lowest in my initial board, that is before I even deleted anything, even then if it was the lowest, let's say like this wall or this wall or this wall, so they are the lowest in the column initially also, so they are definitely breakable. So we will add an edge from here to here always. Okay, Like when we are trying to do a BFS, we will always visit here. Okay. But now the thing is that since this wall is breakable, like since we reach here, the main observation here is that since we are able to reach here, we would be able to reach every cell of this column. Do you get me? Like if we are able to break the wall like this and go into this cell, then it is pretty easy to see that we would be able to reach every other cell on this entire column. I mean above this, right? Like if we are able to reach here, then we are able to reach at every cell. So actually we don't care that do we come from here or not. Like okay, that it is true that if we come from this path, then we cannot reach here, but if we come from here, then we can reach here, right? That is for sure. So actually, like there is at least one path via which you can reach this cell, and therefore the answer for this would be 1. Okay, so basically whenever you are like destroying a wall which is like the lowest wall, then you can actually visit all of the other cells in that column as well. Like in your BFS, whenever you are doing this, like whenever you are moving from a cell to a wall, and that wall is the lowest wall in the column, so you can destroy it, right? And since you have moved there, you also know that you can move into here, here or here as well, like just by going upwards. So actually just visit them as well, like these cells, this one and this one, just visit them also, like insert all of them in the queue. Okay, and other than that, just simply do your BFS. Like always move into the empty cells, that is for sure, and for the wall cells, only move into them if they are the lowest. Okay, and if they are the lowest, then also insert every other cell in the column. That's the algorithm, because you will know that you can definitely reach these cells somehow, right? So this is why the algorithm works. That is the main idea here, that we just want to know that can we reach this cell or not. Like we just want to know that can we reach this cell or not. We don't care about the path, right? So actually we know that since we can reach here, we can definitely reach here. So we will again we will just put all these cells into our queue also, and like start a BFS from them also, right? So yeah, that is the entire logic. Like it was a bit tricky to think of, but it is very elegant, right? So I hope you understood this logic, why it works. And if you didn't, then you can like DM me on Codeforces. Like if you go to Codeforces and log into your account and search for my handle Prady. Okay, a typo was there, Prady. So you can send me a message. Okay, send message option is there. So you log in and then click this. So like you can send me a message on Codeforces if you have a doubt. Okay. So yeah, this was logic for problem E, and I'll show the code for it as well. So we have NC, C in NC, and C minus minus because zero indexing. Okay, they have given one index, but I want zero index, so I'll do C minus minus. Then string S of n, and I'll input this board, right? And then also I'll pre-compute the lowest basically the lowest wall for each column. Like whenever I encounter a wall, I want to check if it is lowest, right? If it is the lowest, then I will go into it, right? So for that I will need to know that which wall is the lowest, right? So I will pre-compute that, like for I equal to 0 to n minus 1, for j equal to 0 to n minus 1, if s of ij equals to hash, then lowest of j equal to I. So like if there are multiple hashes in the column j,
then the last value to be set would be the maximum value, like because I is going from 0 to n minus 1. So this is how the lowest, as in numerically the highest wall is counted, right? Then I'll just have a BFS. So vector of vector visited, like a 2D boolean vector visited. Then we start from n minus 1 comma c. So visitor of that equal to true, and my q dot push n minus 1 comma c. And then I have my answer, that am I able to visit the first column or not. Like I don't really need this actually, but okay. So while q dot size, the current element is xy, q dot pop. If the row equal to 0, that means we have reached the top row, so we won't continue. But ans of y equals to 1, that is we can reach this column y in the top row and continue. Otherwise, we will check all the three directions. That is, let's say if we are at y right now, right? So we'll check y minus 1, y and y plus 1. Like my new x would be x minus 1, and my new y can be y plus 1, y minus 1, or y, right? So if new y is less than 0 or greater than equal to n, then we'll continue. If we have already visited this node, then also we'll continue. If it is empty, then we will put it into the queue, right? And if it is a wall, then we'll check if it is the lowest one. So if the lowest one in this column, that is new y, if that is new x, like if this wall is the lowest one, then we will insert all the nodes. Like we'll insert, let's say if we are moving into this node, so we'll insert this one and all the nodes above it as well into my queue. Okay. So for j equal to new x, j greater than equal to 0, j minus minus, I'll insert j comma new y if it is not visited yet. Okay. So this is the logic for this problem. And then finally just print the answer, where ans is the string in which we are marking 1 whenever we reach the top row, right? So this is the logic for this problem. Okay. So yeah, that is it for today. I hope you understood the problems, and if you did, then if you didn't, then you can DM me on Codeforces, like whatever your doubt is. And yeah, thanks for watching. I'll see you guys next time. Bye bye.